Now let us see an example. Okay, so how to get or how to find out physical address of particular if you have the logical address. Okay, so in this example, say suppose the size of the main memory is 32 byte and say page size is 4 bytes each. Okay, so this main memory is 32 bytes entire thing, and each page size is your 4 bytes. Okay, so here I can say this one is of 4 bytes. This is your page. Okay, this is some process p1, so it is divided into how many pages here? 1 2 3 4 pages. I'll write here for your understanding. Page 0, this is page 1, page 2, and this is your page 3. Getting it? Now again your each page is divided, right? Why? Because it is, we are assuming here each page is of 4 bytes. That means you have 4 bytes instructions present here, right? 0th byte, first byte, second byte, third byte, likewise. So each page is of 4 bytes, right? Again, how you have to, you can see here page number 1, it has the byte number as 4567, but how you have to read it is, this is location 0, location 1, location, I'll write here location 1, sorry, 0, 1, 2, 3. So each 4 bytes, it would be again divided into 1 bytes each, right? And the lower address would be 0 always. Fine. Then we have this page table. So they have given the mapping, like which page would be present in which frame. Then we have this main memory, right, which is of 32 bytes. So you have to divide 32 bytes, right? How you divide? So we all know that each page size is equal to the frame size. So even your each frame should be of 4 bytes each. Then how many frames will be there in the physical memory? So what you do? The entire your 32 bytes, okay, the physical memory size, you divide it with the size of your page, that is 4. So you should have 8 frames in your main memory. Do you have 8 frames here? 1 2 3 4 5 6 7 and 8, right? So we have 8 frames of 4 bytes each. Remember, the main memory is divided into 8 frames of 4 bytes each. Okay, 4 bytes each. Why? Because the page size is 4 bytes. Now let us see the page table here. So we know these are the page numbers, right? Page table, this is your page number and this is your frame number, right? This is P and this is F. Fine. So now read the page table. How do you read this? So page 0 is present in frame 5, page 1 is present in frame 6, page 2 is present in frame 1, page 3 is present in frame 2. Right? Now you check your physical memory whether that is correct. Check the contents of page 0. What is the content of page 0? A, B, C, D. Now this page 0 is in the frame number 5, right? Check the 5th frame. You have to read. Why? Because we have started from your 0. Check or consider this as your frame 0, 1, 2, 3 up to 7. Okay. This is frame 0. Why? Because page 0 we have started, right? That's why frame 0 till frame 7, that means 8 frames together. Now check the 5th frame. 0th frame, 1st, 2nd, 3rd, 4th, 5th. Right? So page 0 content should be present in the frame 5. The ABCD is present here. Then the contents of page 1, that is EFGH, it should be present in frame 6. It is present in frame 6. Content of page 2, that is IJKL, it is present in the first frame, and the last one, page 3 content should be present in your frame number 2, MNOP, which is also present. So now we know like how your mapping will be done. If suppose you are asked to calculate the physical address, say suppose you have been given the logical address, then you have been given all these things, right? What is the total size of your memory, this page table mapping, as well as each page size has been given. Then how do you calculate the frame size, right? If suppose the logical address, okay, the logical address given to you is 0, or suppose basically say if I want to access this particular instruction A, from the page 0. That means from the fifth location I have to access this particular instruction, and CPU has to execute only that instruction. Say suppose, okay. First, the logical address has been given to you, which is 0. Fine. Okay, logical address 0, it means it is in the secondary memory. So, logical address 0 is your page 0, and you have a offset, right? Offset as 0. This D, offset D is 0. Why you have this D as 0? Why? Because from the starting or the lower address, check its range where it has been present. It is present at the 0th location, right? That's why the offset here will be 0. Then how do you calculate this particular, physical address of this A in the main memory? So for that, what you have to do is, first you have to check the frame number where your this particular page is present, or this location or logical address 0 is present. So A is present in page 0. Just check in which frame it has been present. It is present in the fifth frame, right? So fifth frame, then you have to multiply this frame number with the size of each frame. What is the size of each frame? That is 4 bytes, right? Then what you have to do? You have to add the displacement or the offset. So offset is how much here? A. It is 0, right? So add 0. How much you'll get? You'll get 20. Now 20 is your actual physical address or main memory address in which your instruction A is present. Just check whether A is present in the location 20. So A is present in location 20, right? Now say suppose you have been given the logical address as 1. Okay, I'll write here the logical address is 1. Fine. What is the displacement now? So it is present at the first location, right? 0, 1, 2, 3. The location or the range is 1. Fine. So for the logical address 1, what is the frame number? It comes under page 0, right? Again, it is the fifth frame. So 5. What is the page or the frame size? It is 4. Then what is the displacement of the logical address 1? It is 1, right? So you should be having the value B or this instruction B at the location 21. Okay, we have here, it can be written as 20, 21, then 22, 23, right? So your B is present at the location 21, which is also correct, right? Now let us take one more example. Okay, so this was quite easy, right? So I'll give you this example like 15. So if your logical address is, say suppose it is 15, then what you have to do is check first the page number where it is present. It is present in the location, or sorry, page number 3. Come to the page table and check the frame number. Page 3 is present in frame number 2, right? Where is our frame number 2? 0, 1, 2. This frame, right? Now what you have to do is like this frame number, which is 2, it has to be multiplied with the frame size, which is 4. Then it has to be added with the displacement. What is the displacement here? So this is your, even if the address is 12, 13, 14, 15, so as this is because on new page, okay, so you have to consider like this: 0, 1, 2, 3, right? That means for the logical address 15, so the displacement is 3. So do this one: 8 plus 3, which is 11. That means your instruction P, it should be present in the location 11. Just check that. So M is present in 8th location, N is present in 9th location, O is present in 10th location, and P is present in 11th location, which is correct, right? So for the logical address 15, or basically, yeah, for the logical address 15, what will be done is the physical address 11 is obtained, and then in that 11th location our instruction P is present, right? And now the CPU can execute this particular instruction. Fine. So this is an example. Now let us consider one more diagram. So this diagram, it basically shows you how your frame list would be there. What are the free frames before allocation of a page to that particular frame and after allocation, which is quite easy. Okay. So say suppose in the main memory, so we have these many free frames like 14, 13, 18, 20 and 15. Fine. So and suppose we have a process P1 which has 4 pages 0, 1, 2, 3. Now this process P1 or the pages in this process P1 has to be loaded into say this free frame list. So how this loading is done is like it is not contiguous in any way, so this page 0 can be kept in location 15 or the frame 15, page 1 can be kept in frame 14. Why? Because it is non-contiguous, right? Paging comes under non-contiguous memory allocation. So this process, this is this diagram, A diagram, this is before allocation, right? Now say suppose your operating system has allocated the frames like page 0 is present in frame 14, page 1 is present in frame 13, page 2 is present in frame 18 and page 3 it is in the frame 20. Now out of 5, 4 pages, out of 5 frames, 4 frames have already been allocated. So only free remaining is the 15th frame, and this might be any other process, okay, pages of any other process. So you have to understand one thing here is in paging, as it is non-contiguous memory allocation, your process is divided into multiple pages and those pages can be loaded anywhere into the free frames that are present in your main memory. Getting it? So next we will talk about the hardware support or how we can implement this particular page table. So page table has to be implemented somewhere, right? So that your operating system can access that, right? So the hardware implementation of your page table, it can be done in many ways. So the simplest can be your the page table can be implemented using the registers. So these registers should be built with very high speed logic to make the paging address translation efficient. So the use of the registers for the page table, it is satisfactory only when your page table is very small, like about 256 entries. So, but if you have more than that, like 1 million entries in your page table, the register building of your page table on the registers is not efficient. Okay. So instead of that, your page table would be kept in the main memory itself and a page table base register, right? We call it as page table base register. This would be, or this particular register, it would point to the page table which is inside your main memory. Okay, so it is like your page table is there, right? So this page table, it will also be kept in the main memory itself. Okay, and you have a page, we have a register called as page table base register, and this register, it would point to the location where your page table is present inside the main memory. Fine. Now the problem with this approach is that the time required to access your memory location. So we have a solution for this, that is, for this we can use a special small fast lookup hardware cache called as TLB, that is translation look aside buffer, right? So TLB is the solution for this one. So TLB is a fast lookup hardware cache. It is small. So this translation look aside buffer is the solution for this one. So here again the TLB is high speed, and each entry in your translation look aside buffer TLB, it contains two parts. So in this diagram you can see, right, this is your TLB, right? So just a minute. So here you can see the TLB, right? So this TLB translation look aside buffer, it contains two parts. One is the key and another one is the value. The key or the tag is your page number and the value is the frame number. Okay. So your TLB, it contains two parts. One is your key, or it is also called as tag, and another part is value. So key is nothing but your page number, value is nothing but your frame number. So whenever you do a search in this TLB, it is comparatively very fast, but it is very expensive. So basically the number of entries in a TLB is small, often it ranges between 64 and 1024. This TLB is used along with the page tables, like, so we'll see how this TLB it can be used along with the paging or the page table. So first what happens, as usual, your CPU, it generates some logical address. That logical address is divided into two parts. One is your page number and the other one is the offset or the displacement, right? First what will be done is this page number is given as input to this TLB. You can see this arrow right here. So first your operating system, it searches the page number in this translation look aside buffer. So if the particular page number is present, its corresponding frame number also will get, right? So say suppose the page number generated by your CPU or the logical address is divided, right? Say suppose it is 2. Okay, say suppose the page number is 2 and we have the frame number as here 5. Okay, if suppose your operating system finds that first basically TLB has to be searched, then only we'll go to the page table. Do not first search the page table, right? So first the page number is searched in the TLB, its corresponding frame number we will get. So if we get this one, if we get the particular frame number for the page number, we say that it is a TLB hit. That means we have got the frame number for the page number. So then what can be done is that particular frame number which we have got, that can be added with your displacement. Then what will we do? We'll get the physical address, right? This is quite easy. This is the first process. The page number is first checked with the TLB, corresponding frame number is taken, and that is added with your offset and we'll get the physical address. If suppose this page number 2, say it is not present in the TLB, suppose this is not the right, page number 2 is not present in your TLB, then what should be done? At that time, it will be called as TLB miss. Okay, fine. TLB miss, it means the page number, whatever that has been generated, it is not present in the translation look aside buffer. Now what has to be done is the page number, it has to be searched in the page table. So whenever there is a TLB miss, that means you did not get or the particular page number is not present in the TLB. Next it has to be searched in the page table. Again this page number will be given as index to the page table, right? We'll see or we'll get the corresponding frame number from the page table. Again the process is same. The frame number which we got from the page table is added with the displacement or the offset, and then once we get the particular address, that would be our physical address, so that the CPU can execute that particular instruction. Fine. So this is about your translation look aside buffer. Now if suppose our TLB is also full of entries, then what will be done? Then your operating system, it selects one of the entries for the replacement. So again this replacement would be based on some policies. Okay. That's it for today. We'll conclude our session. Thank you.